Hello sir, my name is Karthik and my roll number is 21ME61R12. This video is being recorded as a solution to the assignment problem on friction stir welding that has been given to us. I'm going to straight away dive into the steps that I took to set up the problem. I would also like to mention that this simulation has been done on an AMD Ryzen 7 machine. So the first step that we take is the geometry creation in design modeler. So we started with the XY plane. We created a sketch in XY plane. So we created a circle of 240 diameter, and then we created two lines to define our geometry. We gave dimension to these two lines, which is 144 The square part of this geometry is 144 and then we generated this geometry. We created another sketch to create the pin. So we created a circle here and gave it dimension as 6 since the dia of pin is 6 Now to yes, the dia of pin is 6 So now we need to create the space for pin. So we in the extrude settings we need to cut the material but in reverse direction. So we cut the material for 5 We cut the material up to a depth of 5 in reverse direction. Now this is the reverse direction into the material. For sketch 3 we created another circle. Now this circle is for the shoulder diameter. This is the shoulder and the shoulder diameter is 24 Now in the extrude settings we do not require to cut the material. We want to imprint faces so that this and this surface can be separated. Now the next step is named selection. We created named selection so that we can define the surfaces. Now we defined this surface at velocity inlet, this as pressure outlet, this is the FSW tool, the shoulder part, the pin area, this hole as the top surface, and the bottom part as bottom face. So all the faces has been created. Now the geometry is complete. Now we go to the mesh part. Now as per the problem, we are required to use an element size of 0.2 with a maximum element size of 1 So for face sizing we used an element size of 0.2 with a growth rate of 1.15. Now when a growth rate of 1.1 was used, the maximum number of cells the maximum number of tetrahedral cells exceeded the maximum number of cells which are allowed in the student version of Ansys. So we used 1.15 here. For the edge sizing, this is the edge. For the edge sizing, we used an element size of 1 mm and the default growth rate of 1.2. Now using these meshing parameters, we created the mesh. So it looks something like this. Now let us come to the setting up of problem. Now we selected pressure based, velocity formulation is absolute, and the time is steady. The energy equation is kept as on. The viscosity is this viscous model is kept as lamina, and the viscous heating, because it is in thermal analysis and there will be heating, so we check the box for viscous heating. That's it in the model, and we created a fluid in the material. The density of the material is created as 2700 kg per meter cube. The specific heat, this specific heat and thermal conductivity has been given to us in the problem statement. So we are required to use the 4 coefficients, and so we selected 4 coefficients. We used 4 coefficients. Now these values has been given to us in problem statement, and specific heat will be automatically defined as soon as we specify these coefficients. Same with the thermal conductivity, it's a polynomial, and similarly 4 coefficients. The viscosity model is the non-Newtonian power law, so we select non-Newtonian power law here. Yeah. Now the boundary conditions. Velocity inlet, we specify this velocity magnitude as 0.00133. Now this comes from the welding speed, 80 millimeter per minute. So we change this into meter per second, which comes out to be 0.00133. The velocity direction specification method has been selected as magnitude and direction. So 100, which is x direction basically. Similarly with the pressure outlet, the gauge pressure has been selected as 0. The direction has been selected as 100. Yeah. Yes, this is an important part. So we specified the parameters for the bottom wall. So the bottom face is a moving ball but translational. the direction is specified as 100, which is x direction. The speed is the welding speed. This is the welding speed in meter per second, and a no slip condition has been specified. So the bottom wall, a convection will occur on the bottom wall, and a heat transfer coefficient of 10,000 has been selected. Since most of the convection will take from the bottom wall, so that is why this value is taken as 10,000. For the tool, it's rotational. The tool is rotating, so it is taken as the motion of tool is taken as rotational. The rotational axis is taken as the z direction, and the tool is rotating at 810 rpm, which comes out to be 74.351 radian per second. No slip condition has been taken here as well. For the top face, it's a moving ball, translational. This is the welding speed, x direction, pretty much the same. The convection heat transfer coefficient that we chose here is 30 watt per meter square Kelvin. Now this is way less than what we chose for the bottom wall, because very less convection occurs from the top face. Now that's it. Now in solution, we report definitions. We created these report definitions, 4 definitions: lateral force, thrust force, torque, and weld force. So for all these 4 report definitions, the plot and the data will be given to us after the analysis. So before running the actual calculation, we need to initialize the problem so that it creates an initial solution. So we click on initialize, and we are doing a hybrid initialization. Then we run calculation. So this is our element size 0.2, and the growth rate is 1.15. The number of tetrahedral cells is this. The number of iteration it took is 475, and the time it took is 39 minutes. Peak temperature is 592. Torque is 37.923. We calculated the torque here. And using this torque, we calculated the power requirement. So the power comes out to be 2.82 kilowatt. So we also did the simulation using the cells element size of 0.3, 0.4 and 0.5. The growth rate is 1.1 in all the 3 cases. Thus, as we now it can be seen here, as we increase the element size, the number of iterations that it takes to converge is less, and the calculation runtime is also less. For element size of 0 0.2, it took 39 minutes to converge the solution, and for an element size of 0 0.5, it only took 8 minutes. The peak temperature is almost similar in all the four cases. There's not much difference in torque, but it can be seen that the smaller element size that we use, the more accurate solution we obtain. Now this is the temperature plot, and as it can be seen, the highest temperature is 592 Kelvin here. The temperatures around the weld zone is less than 592. It can be seen that it's 446, something around 446 or 430, this green part, and the ends, they are 300 Kelvin, which was the temperature that we chose. It's the material temperature. Now this is the molecular viscosity plot. We know as we heat a material, the molecular viscosity decreases. So this blue part, this blue contour shows less molecular viscosity as compared to the red part. This is the contour information. In this part, the molecular viscosity decreases because of the heat, produced by the friction. We also calculated the forces. This is the thrust force on the tool, 5.77 Newton. The lateral force is 7.11 newtons, and the welding force is 19.57 Newton. So this is all the data that we obtained from this simulation, and the most interesting thing that I got to learn from this study is how we can carry out the process on a software, and the amount of data we obtain, so that we can analyze the data and optimize the parameters for better process efficiency and also a better product. Thank you.